All right, let's break down two of the most fundamental forces in the universe, electric and magnetic fields. We're going to cover what they are, how they behave, and the key equations that really describe them.
So here's our game plan. We'll kick things off with the basics of electric fields. Then we'll jump into how they're used to store energy in capacitors. After that, we'll look at the forces created by magnetic fields, and we'll wrap it all up by seeing how these two fields are beautifully interconnected through electromagnetic induction.
So first things first, what even is an electric field? Well, you can think of it as a region in space where any charged particle that enters it is going to feel a force that acts on it without anything physically touching it. And to measure this, we use something called electric field strength, which we represent with a capital E. It's kind of like a measure of how strong this invisible electrical wind is at any given point, how much of a push or pull it exerts on a charge we place there. The relationship here is super straightforward. The electric field strength, E, is simply the force, F, that a charge experiences divided by the size of that charge, Q. This is our core foundational definition. So where does this force actually come from? That's described by Coulomb's law. It tells us the force between any two charges depends on how big the charges are, and this is the crucial part, it gets weaker with the square of the distance between them. So if you double the distance, the force drops all the way down to 1/4 of what it was. And here's what that looks like as an equation. The force, F, is proportional to the two charges, Q1 and Q2, multiplied together, and it's inversely proportional to the distance, r, squared. Now those other symbols, the 4, pi, and epsilon naught, they're just constants that make sure all the units work out. That epsilon naught in particular is actually a fundamental constant of the universe, called the permittivity of free space. Okay, so now that we've got the principles down, let's see how they lead to something really practical, storing energy. This section is all about electric potential, the uniform fields you find between parallel plates, and the device that makes use of them, the capacitor.
On this slide, you can really see the difference between two main types of fields. On one side, you have a radial field coming from a single point charge. It radiates outwards, and it gets weaker the further you go. But on the other hand, you have a uniform field, like the one between two parallel charged plates. Here, the field has the exact same strength everywhere, which is why we draw the field lines as perfectly parallel and evenly spaced.
And for that special case of a uniform field, calculating its strength gets a lot simpler. It's just the potential difference, or voltage V, between the two plates divided by the distance d that separates them. This brings us to capacitance. It's really just a measure of how good a capacitor is at its job, storing charge. So a capacitor with a really high capacitance can hold a ton of charge for every single volt of potential difference you apply to it. And the equation for it shows this relationship perfectly. Capacitance, C, is equal to the amount of charge it's holding, Q, divided by the potential difference, or voltage, V, across it. All right, so we've defined what a capacitor is. Now let's see what it actually does in a circuit, specifically how it stores and then releases energy. The energy that gets stored in a capacitor, which we label W, can be calculated in 3 different ways, and you can see them all here. The great thing is, all 3 equations are totally equivalent. You just use whichever one is most convenient based on the numbers you have, whether that's voltage and charge, capacitance and voltage, or charge and capacitance. So here's what's happening during the charging process. It's a pretty dynamic sequence. As charge starts to build up on the plates, it creates its own voltage that actually pushes back against the power supply. This opposition makes the charging current get smaller and smaller, until finally the capacitor's voltage matches the source's voltage and the current stops completely. Discharging works in a similar way, following this exponential curve. The charge, Q, at any given time t, is just the initial charge it started with, Q0, multiplied by that exponential decay factor. That little RC term in the exponent is really important. It's called the time constant. It literally tells you, in seconds, how quickly the capacitor discharges. A bigger time constant means a much slower discharge. Okay, let's switch gears. We've been talking about static charges, but what happens when they start moving? Well, that brings us into the world of magnetism, which at its heart is all about the movement of charge. Now here is the absolute key takeaway. A magnetic field only exerts a force, F, on a moving charge, and the size of that force depends on the magnetic field strength, B, the charge itself, Q, how fast it's moving, V, and the angle, theta, between its velocity and the field. The force is strongest when that charge is moving totally perpendicular to the field. So how do you figure out the direction of this force? For that, we use Fleming's left-hand rule. It's pretty cool. You just take your left hand, point your first finger in the direction of the magnetic field, and your second finger in the direction of the current. When you do that, your thumb will automatically point in the direction of the resulting force or motion. And what works for a single charge also works for a whole bunch of them flowing together in a wire, right? That's just a current. So we can scale this idea up. The force, F, on a wire depends on the magnetic field, B, the current, I, the length of the wire that's inside the field, L, and again, that angle theta between the wire and the field. And for our final section, we get to the really profound part, the deepest connection between these two forces. This is electromagnetic induction. It's the incredible principle that a changing magnetic field can actually create an electric current out of thin air. This whole phenomenon is governed by two main laws. Faraday's law tells you about the size of the induced voltage, or EMF. It says the voltage is proportional to how fast the magnetic field is changing. Then you have Lenz's law, which tells you the direction of the current, and it always flows in a way that tries to fight against the change that created it in the first place. This is the classic way to see Lenz's law in action. As the magnet falls toward the coil induces a current that creates a magnetic pole to repel it, slowing it down. Then, as the magnet passes through and starts to leave, the current actually flips direction to create an opposite pole to attract it, again slowing it down. This is conservation of energy right there. The kinetic energy the magnet loses is what gets turned into electrical energy in the coil. And this equation right here ties both of those laws together. This part on the right, the number of turns in the coil, N, times the rate of change of magnetic flux, that's Faraday's law. And that little negative sign out front, that's the mathematical way of writing Lenz's law, representing that opposition to change. So we'll end with this thought. For centuries, people studied electricity and magnetism as two totally separate things. But as we've just seen, they were so deeply linked you can't have one without the other. A moving electric charge creates a magnetic field, and a changing magnetic field creates an electric field. Realizing this was a huge step toward understanding that the fundamental forces of nature might just be different faces of a single unified whole.